started working out calculations on equations of state. And if you remember, we looked at 3 equations of state yesterday. And can someone remind me some of those equation of states? So we looked equations of states. What equations of states did we look at yesterday? What equations of state did we look at yesterday? Can someone remind me? You can just put it in the chat. All right, okay. So yesterday we looked at Van der Waal equation of state. We looked at ideal gas laws, and we looked at virial equations. So those were the 3 we looked at yesterday. And we said that equations of state, what they do is they relate pressure, volume, and temperature together. So they relate those 3 parameters. That's what equations of states do. And then we also emphasize the fact that ideal gas does not capture everything that happens in reality. So that's why we have the others, the other laws. So every other law we've been looking at, apart from the ideal gas, they describe real gases. So let's look at the question we've got here. Says calculate the compressibility factor and molar volume. So we are looking for, so compressibility factor, that is Z, and the molar volume for methanol, that's your specific molar volume V for methanol vapor at 500 K. So we know 500 Kelvin, that is temperature, and 10 bar. So 10 bar, that is pressure. So we have all those there. And then we've been given the virial coefficients, the B and C. We've been given those values. So then we are left with, we've also been given the critical temperature and pressure. We need critical temperature and pressure for the calculation for the Rayleigh-Kwong equation. So those ones are needed there. And the AB, the virial coefficients, those are needed for the 3-term equation. They are needed for the 3-term equation. So we'll need those values there. So as we always say, put down the things you've got and then put down the things you're looking for. So from these 2, so these are the 2 equations that are needed. So the truncated, as we talked about yesterday, the truncated form of the real equation that has to do with the 3-term. And 3-term, when you have those 2 coefficients, B and C, that's your 3-term virial equation. So that's what, and we are looking for, and from the question you're looking for Z. So that's what we're looking for both of them. We are also looking for, what else are we looking for? We are also looking for V for both of them. So let's move on to the solution. So let's look at what we've got. We've written them down. For consistency of unit, bar needs to be converted to Newton per meter squared, because if you look at all the other things in the equation, or all the other parameters we've been provided with, we'll see units like Newton and meter there. So that's why we've done this conversion. So we have that, and then we've been given these B and C values. You've also been given critical temperature and critical pressure. Please don't confuse them with the temperature and pressure we'll be looking at later on. Don't confuse those things. So you see this is TC, that is PC. They are 2 different things. We talked about them at in the lecture 2 weeks ago. So please, those are 2 different things. So let's move on. We'll start from the truncated form of virial equation. We have this, we have the equation for us, which we can rearrange until we make V the subject of the formula. So there. But remember, as we said yesterday, that when it comes to any quadratic equation, if you look at this as well, so we're looking at this having V to the power of 2, that makes it quadratic. Also here, you see we have a t raised to the power of 0.5. So whenever we have those quadratic expressions, we've said our v needs to be calculated using iteration. So we try different things until we get to the optimum. And the v at the optimum, that is what we then use to calculate our compressibility factor. So moving on, so if we make V the subject of the formula, we plug in all the values that have been provided. And if you remember from what we did yesterday, we said when we are dealing with virial, RT over P, if you still remember, that is also the V naught, or the V for your ideal gas. V naught, or the V for the ideal gas. So that is the V value, which we'll be using. We use it consistently throughout the iterations. We use that value consistently throughout the iterations. And also we said for subsequent iterations, we use previous value. Can I say that again? For every subsequent iteration, you use previous value. So when you're dealing with V1, you use V naught to start. When you're calculating V2, you use V1 to start. But when it comes for all your iterations, this remains constant. So that remains constant, and then we keep varying the V value. So that's what we do. So moving on, so we have this expression. So these two expressions are what you'll be using to. So the first thing you always want to do for yourself is um, get the expression you'll be using for your iteration, and then you just be plugging in your values and make the variation. So that's what we've got. So the very first one, we plug in our RT over P value, which is there, and then we have that is 1, B, and then we have C. So B and C. So we have our B, we have our C, and then we're looking for. And so we start with the first iteration. Remember, for the first iteration, we substitute V naught there. We put V naught there. So there, so V naught, and V naught, that is the V value for ideal gas. So we've plugged in those, and then the first value we've got, V1. So if you look at the value of V naught, V1, which is 3.934, compare it to V naught, this value, you see that it is not equal. I mean, they are not equal rather. So your V naught and V1 are not equal. What does that infer? You continue, you iterate again. And now when you're iterating next for this subsequent value, what do you use? You use the previous value, V1, for you to calculate V2. So if you come here, this is our working expression. Always have the working expression for your iteration. So the same story, the V1, we plug in the V1 value. This remains constant. The RT over P remains constant. This, we keep varying this. I mean, we keep varying this, which is same. So you calculate that again, we get our V2. So if you have to compare the V2 to V1, again, V2 is not equal to V1. So what does that mean? We iterate again. So V3, for V3, this that goes there. So the value goes in there. Let's move on. So we do the calculations. We have V3. If you look at the value of V3 and V3 and V2, if you look at those values, you see that they are quite close. 3.9, so it's quite, we are almost there. So V3 and V3 and V2, we can say are approximately the same, very close. So if you iterate one more time, we plug in those values here, and then we get V4. So if you look at that, V4 equals V3. So that means, like we showed yesterday, we've reached the optimum. So we've reached the optimum. So the V value, there, which is our optimum. So since we've reached the optimum, we can then use that, plug that in into our expression here to calculate the Z, the compressibility factor. So Z equals to PV over RT. So remember, so you can, it's either you start this calculation all over again, or you simply just go back here where we already have the value of RT over P. RT over P. So if you have RT over P, it simply means that we equally have P over RT, where is we equally have P over RT, meaning inverse. So that is that multiplied by the V value. So that is the V value, and that's how we get our Z there. Is that clear? To any question before we move on to the next one? Any question before we move on to the next one? So by now we've solved about three or four iterations. So by now you should be able to get a good grasp of how we do iterations to calculate our volume. And we've also justified the reason why we need to do that. For every quadratic expression, you can't solve it the same way you solve straight line expressions. So you need to use iterations. Are we all clear? Can I move on? Can I take that as a yes from the class? Can I have response on the chat panel, or you unmute yourself? And all right, okay. So let me just take silence as consent. Thank you, Uwe. Thank you. So let's move on to the next one. Thank you, John Matthews. Red Lake Kwong equation, you could see, like we mentioned yesterday, these are definitely people's names. So hopefully one of you also will make something big in the nearest future, and will be mentioning your names. Be mentioning Wolve equation or Lombard equation or Benklin equation. All right, so moving on. So we've got the expression, we've been given this, and also remember we are looking for V. It's V we are looking for. So the very first thing we need to do is we need to calculate our A and B value. We need them here. We need them there. We want to start from that because we already have the things needed to calculate A and B values. And those are the critical temperature TC, critical pressure PC. So we've got those ones. So if you plug those values in, we have our A value, we have our B value. So we have those in. So we have those in. So the next thing is we want to simplify this equation. So you want to simplify that equation. So we simplify. So simplify, excuse me, and also want to make V the subject of the formula. Make V the subject of the formula. So we do that. So we have that expression. Remember, as I said, one thing, you always want to have your working expression, and that which you use for your iteration, and that's what you'll be using throughout your iteration. So we have those values. We have so okay, to reiterate again, let me just reiterate that there, just reiterate. So just to reiterate, T and P value are not the critical values. Remember, critical values are TC and PC, and we need those values just to calculate our A and B. But the real T and P are the ones you use for your equation of state. So remember that, use them for the equation of state. So moving on, so let's move on that. All right, so we have our V value. So we've said this is our working expression, working expression. So we plug in our values, RT over P, which is there, and then B, plug in every other thing, A, that is A, V minus B. So V minus B, you have that there. And then you have T raised to power 0.5, P, V, we are looking for V. So we have those. So again, we simplify until, so this should actually, let me come back. Let me rather do this here. Let's rather make this a working expression. So this is a working expression or equation. So we have a V value that we'll be looking for. We have those who will be varying. Oh, so let's start from the very first one. For the first one, like we said, remember the first one we start with the ideal gas value V naught. We've calculated V naught in the prior calculation. So we're not, remember we have a V naught from here. This is our V naught. So that's what we'll be using throughout. So since all the equation of states, they are based on ideal gas, so that's why for that same gas that we'll use, since we're still dealing with the same gas, is the same V naught that we calculated in the previous equation of states that we'll be using for this particular equation of states. So let's move where were we? Okay. So we come here. So V1, so that is our V1. We just plug in that value. We have this, so there, V naught, we have a V naught from the previous calculation. So that's our V naught. We have this there, V naught plugged in back there, V naught. So we have a V naught. So we have V1 value. So take note, V1 value 3.974. We move on. Same story. Remember the V value, we use V1 to calculate V2, subsequent for the next, subsequent for the next. So that is iteration. That is why it is called VI plus 1, subsequent for the next. All right, so V2, same working expression that we've been using, but now with the V values will be V1. V1 from here, V1. So those are our V values there. Calculated again, we have our V2, 3.964. So if you are to look at those values are not equal. So we are saying V1, so yes, since we didn't do the previous one, we can say, let me put that clearly. So we can say V naught is not, V naught is not equal to V1, is not equal to V2. But we can see a trend that it's decreasing. So let's move on. We can see a trend that it's decreasing. So we same story. For V3, we use V2 values here. We use our V2 values there, and then we calculate our V3. So we got our V3. Let's look at how close. So quite close, V3. And so we are almost there. So we can say V3 is almost equal to V2, but it's still not equal to V2, but it's almost equal. And considering the fact that those values, the difference is negligible, we can fly with that. We can use that V value because it's quite negligible. Remember, it's to 10 raised to power minus 3. So it's like saying it's 0.001. So the difference between these two is 0.001 times 10 raised to power minus 3. If you put that out, that is quite negligible. So that's how we got our Z there. So that's how we solve that. Any question? And looking at this again, as we've been emphasizing, if since the z is less, the z is not equal to 1, it emphasizes the fact that we are dealing with real gas. Any question?